BC Calculus, Lesson 2.2, Limits Involving Infinity. So things get more complicated in the second lesson, and I thought things were pretty complicated in the first lesson. This will be a theme all year, so just get used to it, which is really important to learn something thoroughly because you're going to build on it constantly. If you don't know your limits and then you get to integrals and you say, well, I never really understood limits, well, you're going to have a problem. So let's talk about it as we get out to infinity. So let's do a very quick graph. And this is 1 over x, something like this. So here we go. What's the limit as x approaches infinity? Of 1 over x? 0. It's getting closer and closer and closer to the 0 line here. What's the limit? And did you see the negative right there? Hard to see. A lot of people miss it. What's the limit as x approaches negative infinity of 1 over x? And that's 0, because here and here they get closer and closer and closer. Well, we already have seen this before. We called it a horizontal asymptote. And we'll just call these HAs. The line y equals b is a horizontal asymptote of the graph of the function f of x if either the limit is b or the limit is b, yada yada. You know what a horizontal asymptote is. This is where the theory and personally I depart, and it'll happen a lot in this lesson. I know what a horizontal asymptote is. Yes, I understand it's a limit. As we get further and further out, we get closer and closer, so it doesn't really bother me. Here's another proof of sine of x using the sandwich theorem. We know that sine of x varies between -1 and 1. So we can take each term and divide by x. And then we can look at this and say, well, the limit as we approach infinity for -1 over x is 0, and the limit as we approach infinity for 1 over x is 0. Since sine of x is between the two of those, we can say the limit, and by the way, a lot of people are saying, I thought the limit of sine of x over x is 1. Yeah, the limit as x approaches 0. Read the full question, please. I may have mentioned that. I may mention that again sometime in the near future. Since sine of x over x is between -1 over x and between 1 over x, it's a sandwich theorem again. It's got to be 0 because they're both 0. It's somewhere in between them. Takes some getting used to. Limits have properties. There's another property we didn't list. I don't need it. I'm writing out your notes just to be a thorough person. I can apply it though. So the limit as x approaches infinity, and you say, we just did something like this. Why are we doing it again? We did not do x as it approached infinity. We can break this into two pieces. 5x over x plus the limit as x approaches infinity of sine of x over x equals 5, because the x's cancel, plus we already know 1 equals 6. And I've been making so many mistakes lately. Yep, just made one. I keep checking my work and catching myself. What did I just yell at you? Don't make the assumption it's going to 0. And then I made the same mistake myself. I'll try and pretend that I did that just to help you. Yeah, right. Now, I don't actually break this problem up. I look at this problem up here, and I say, well, sine of x is just bouncing back and forth between -1 and 1. So it's pretty much going to vanish out of this situation because x is going to get bigger and bigger and bigger and bigger. That -1, 0.1, -0.1 is going to become inconsequential. However, this really becomes a limit as x approaches infinity of 5x over x. The x's cancel. I know I'm going to get 5. So however you want to do it, however it makes sense, works for you, great. But just to be clear, you should look at some of these problems and start to say, well, let me think, what happens here as the bottom gets bigger and bigger and bigger? You should have had practice of this in pre-calc with graphing, so hopefully you did. A note, what if I said, oh, f of x equals the top, g of x equals the bottom, and I said the limit as x approaches infinity of f of x is infinity, and the limit as x approaches infinity of g of x is infinity. Can you take the quotient of those two? And the answer is no. It's not going to work. Can't divide them. So just be careful with the quotient rule, especially when you have infinities in there. If one's infinity and one's not, then it's a little bit more clear. If they're both infinity, got to be careful. So we covered horizontal asymptotes. How about vertical asymptotes? Again, you should know this already. Can't have zero on the bottom. Here's a definition, but it really doesn't help me out personally. Maybe it helps you. Go ahead and take your time and read it. I don't like it. Need to use the definitions because they will bail you out more often than not. But in this case, I know what a vertical asymptote is. Can't have x equals 0. So we have a vertical asymptote at x equals 0, and the limit as x approaches 0 from the negative side of f of x is positive infinity, and the limit as x approaches 0 from the positive side of f of x is also positive infinity. Since they're the same, we could say the limit as x approaches 0 is positive infinity. If they were different, we wouldn't. So this is what it means to describe the behavior left and right of the vertical asymptote. Do not get hung up too much on these. We're trying to introduce the concept of infinity in limits. If it makes sense to you, great, and you're struggling a little bit with the nomenclature, how to write it just right, don't. Be clear, write it out, and we're good to go. Oh, by the way, I'm so smart when I write my notes. I'm not necessarily so smart when I do my videos. What about 1 over x? Can we say that both limits are the same? No, we can't. Since these two limits are not equal here, we cannot say that there's a single limit at x equals 0. We have to keep it as a negative and positive. So how about finding the vertical asymptotes for tangent of x? If it's been a while, I sure hope you go back and review. Tangent looks something like this. You're probably starting to see why trig is so integral to pre-calc, because we use it in regular calc so much. And we would say that the limit as we approach one of those vertical asymptotes, which I'll draw in, would be infinity or negative infinity. It depends on which way. If you're coming from one side, if you're coming from the right, it's actually negative infinity. If you're coming from the left, it's positive infinity. We have some homework problems on that, so graph it out and make sure you read the question. I made mistakes and then I caught myself. But we also can say we have vertical asymptotes at x equals k times pi over 2. K is all integers. No, it doesn't work. I'm sure the complicated formula. So, like I just said, I'm not going to get hung up on the words. K is all odd integers. I hope you knew that z was integers, because I just hope you did. So, what about a polynomial, or an e to the x function, or just y equals x? Well, that is a polynomial. We get way out there in big infinity land. What happens? this graph is kind of interesting. I've got it on the calculator. I'll show you in a minute. Unfortunately, it takes forever to graph. One of them does something like this, and the other one does something like this. And you can see in this range here, they're different at small numbers, close to 0, plus or minus 5 or something like that. They're relatively close to being the same. However, when we get out to really large numbers, negative or positive, they're very, very much the same. You can see the graph down here in the bottom center. I'm not going to hit graph because it literally takes a minute to graph on this lovely calculator. But here they are programmed in. And when I go to table, and I look at them, hey, how about at 0? I get very different numbers. 6 for one of them, 0 for the other. How about 10? All right, they're starting to get closer, and negative 10 is different but similar in that they're pretty far away. How about 100? Let's see if they're starting to get close together. Yeah, they are. Negative 100. And let's try a big number. 10,000. I get 3 times 10 to the 16th. They've gotten so close. And what's going on here? Again, this is how I handle limits. I look at the top, the first highest exponent, and realize that's going to dominate. As we get bigger and bigger numbers, x to the fourth of a really big number is way bigger than x to the third or just x of smaller numbers. So this is what happens. They say, what is the end behavior? The end behavior for, if I were to divide these as something else, the end behavior for both of them for f of x is 3x to the fourth, and I was going to say for large values or of x, or very, very small or very large negative values of x. That's what end behavior means. What's going on out at the big positive, big negative values of x. So again, another definition, if you didn't know, by the way, it stands for if and only if. Whenever I can save time and space, I do. And here are examples of the kind of problems you'll do. Give me an end behavior model. Well, biggest power, forget the rest. Don't have to worry about them. And the end behavior model is just going to be the limit as x approaches plus or minus infinity of that function. Just going to be dividing the first two terms, 2x to the third over 3. Because all the rest are just going to go away. If you sat down and divided them out and see where it took you, you'd get that answer. It's really, it's not that big a deal. It just makes sense to me, so I hope it makes sense to you. The limit over here as x approaches plus or minus infinity. Biggest power is x to the third. They're going to cancel. We're just going to be left with 2/5. You're not sure? Graph it. You'll see. It makes sense. So I hate to be all touchy-feely with limits, but it's just the way I like to do that. A lot of people say, well, it always is the same at plus and minus. Well, yeah, if you have a polynomial, it is. But we might get something else here. What's going on with f of x equals x plus e to the negative x? Well, the limit as x gets really big of f of x gets dominated by x, because e to the negative 10,000 is basically 0. So it just becomes x. And the limit as x approaches negative infinity of f of x basically becomes e to the negative x. Because negative infinity actually gets pretty big for x, but an exponential power grows so much faster. It just blows away an x to the first. It blows away an x to the 50th. You'd have to check and make sure, but it's going to dominate, because now we go to negative negative, where e to the 10,000, that's going to go up way faster than any polynomial function you can imagine. So, not sure about this? Graph it. X plus e to the negative x. look at it, and what do you get? Y equals x on the right, so it's going up the y equals x line. And on the left, it just goes to infinity. It's e to the negative x. It gets bigger and bigger and bigger and bigger. Complicated stuff. We'll sort it all out. Now this is strange. I've gone over this 3 or 4 times. It's just a little bit odd. It takes some getting used to. But you can actually flip everything inside a limit. Flip infinity to 0, 0 to infinity. And then flip the function by going 1 over x. So you can investigate it. So for example, if I said f of x equals sine of 1 over x, and I said find the limit as x approaches infinity of f of x, you could say, well, let's do plus or minus infinity. And we'll leave it like that for now. You could say, what's the limit of sine of 1 over x? So you flip the x and just go to 0 from the positive side. This, of course, is limit as x approaches 0, sine of x, and we'd be able to say, oh, well, that's just 0. It's weird. I'll give you a couple examples. Use this and see if you get it. The problem I had was remembering to put 1 over x in just where x was. It's not an inverse function. It's not this. Just put 1 over x into the function wherever x was. And then it actually makes some sense. Some people also break it up where you go, what's going on as it comes from the negative side, but that doesn't really matter for sine of x. Either way, it's coming towards 0. And that would be equivalent to limit as x approaches negative infinity of sine of 1 over x, which again is basically just 0. Lots and lots and lots to get you thinking. Good luck and happy mathing.